aloha and welcome to my talk. Today we're going to be talking about harnessing weapons of Mac destruction. My name is Patrick. I am a security researcher at Jamf. Previously I was a co-founder at Digita Security, and I'm also the creator of the Mac security website and tool suite Objective-C. So today we're going to be talking about repurposing other people's malware for our own surreptitious purposes. We'll start by showing why this is rather an excellent idea, and then show exactly how to repurpose various Mac malware samples. Of course, we want our repurposed samples to remain undetected, both by Apple's built-in malware mitigations and third-party AV products, so we'll address that as well. Finally, we'll end by covering various generic methods to detect these repurposed creations, because really our ultimate goal is to ensure that Mac users remain protected. So let's dive in. So here we have a diagrammatic overview that conceptually explains the repurposing process. So imagine that Spy A has developed some neat, sophisticated, fully featured malware and has deployed it to various targets, right? Infected various systems around the world. Spy B somehow captures this malware, perhaps either in transit or pulls it off an infected system. Spy B then will take this malware sample to her lab and then repurpose it. So what do we mean when we talk about repurposing? Well, we'll get into this more shortly, but basically we're talking about reconfiguring a piece of existing malware so that you can use it for your own surreptitious purposes. So for example, we can see on the slide, once Spy B has repurposed the malware, she can now redeploy that against new targets, and instead of beaconing back to Spy A's infrastructure for tasking, it'll talk to her new infrastructure instead. Now you might be thinking, okay, this seems like a reasonably neat idea, but why? And we'll talk about two reasons that hopefully show that we should really be asking why not. So first, there are incredibly well-funded, incredibly well-resourced, very motivated hackers, APT groups, and three-letter government agencies that are creating some incredible malware. This malware is fully featured and has the benefit of being fully tested, a lot of times already even tested in the wild. Now I'm rather lazy. I would rather be sleeping on the beach or surfing or doing yoga. So I figured, why not let these groups create this incredible malware, and then we can just repurpose it for our own missions. The idea is to let those with more time, resources, and money do all the hard work. Secondly, if our repurposed creations that we redeploy get captured, it's very likely that they will be misattributed back to the original authors, not to us. This is great. Now you might be thinking, okay Patrick, if this is such an amazing idea, why aren't people already doing this? Well, and the answer is they are. Now I can't comment specifically on this, but leaked slides appear to indicate that the NSA has had this capability for a while. Also, recent reporting from the New York Times claims that the Chinese are doing this as well. Now, to these well-resourced agencies, the benefit of using repurposed malware is twofold. First, it allows them to deploy other countries' malware into risky environments. For example, perhaps a target where another agency, another country, another APT group already exists. So imagine you're the NSA, you hack a high-value target, and you find out, someone else is already there. Obviously, you don't want to put your primary implants on that system. So if you have a repurposed implant that you can use, might as well put that down. Also, we already talked about attribution. These agencies don't like people to know what they're up to. So if they can use repurposed malware, perhaps this muddles the attribution picture. Now, of course, there's going to be challenges to repurposing malware. If there weren't, we wouldn't be talking about it today. But we'll see these challenges are not insurmountable. So first, generally speaking, if we capture a piece of malware to repurpose, we're not going to have the source code for the malware. We're just going to have a binary image. So we'll have to reverse engineer the malware at the binary level. This is kind of the analysis stage, I like to call it. And what we're doing is we're trying to figure out and gain an understanding of what the malware does, answering questions such as how does it persist, how does it install, and what its capabilities are. and of course what command and control servers it talks to. Then with such an understanding, we have to figure out exactly how to patch the malware. Again, usually we don't have source code, so this involves patching at the binary level. Now if the malware talks to a remote command and control server, which most do, we will have to figure out how the malware determines where to get the address of that server, and then also understand the protocol so we can create our own command and control server, so when we redeploy the repurposed malware, we can communicate with our new infected systems. And then finally, since we are repurposing generally known malware, it's likely that Apple or AV products already have detection signatures for this. So we have to talk and we have to figure out how to get around that, because obviously it would be rather unfortunate if you deployed some repurposed malware only to have it detected. Now I want to reiterate that it's very important to take these challenges seriously and get them right, because if not, relatively bad things can happen. Here, for example, we've attempted to comprehensively repurpose a piece of Mac malware, but it turns out that we forgot to modify or patch out the addresses of the backup command and control servers. This means if we deploy what we believe to be a fully repurposed piece of malware, at some point it may beacon back to the original hacker's infrastructure, giving him or her access to our infected targets. So obviously this is something we want to be very aware of and make sure when we are repurposing these samples, we're doing it comprehensively. So now let's talk about exactly how to repurpose Mac malware with the goal of making their malware ours. So the first step is to select a malware specimen, and that is the sample you want to repurpose. This is usually based on two criteria. First, you decide what you need the malware to do, right? Are you looking for an interactive backdoor, perhaps a piece of ransomware, cryptocurrency miner? Take your pick. And then maybe attribution is important to you, right? Do you want your repurposed sample to originally belong to a three-letter agency, a Russian hacking group? So again, if it gets caught, it'll be likely misattributed to them. So on my website, objectivec.com, I have a very comprehensive collection of Mac malware. So that's a great place to start. And all the samples we're talking about today that will repurpose, the original specimens are available for download. Now, once you've selected your malware sample, it's time to analyze it. In terms of repurposing or as we mentioned, the main goal is to figure out things like if it has any remote access, right? If it's talking to a remote command and control server, we want to know what that server is so that in the malware we can modify it to instead talk to us. If the malware does talk to a remote command and control server, we also need to understand the protocol so that we can task it when it connects back to us. And of course, you want to fully understand the malware's capability, both locally, how does it persist, how does it interact with the system, and then also remotely, what commands can we remotely task the malware with. So once you have a comprehensive understanding of the malware, it's time to actually reconfigure or repurpose it. Generally, this means we'll have to patch the malware at the binary level. So here, for example, as we can see on the slide, we've located the addresses of the malware's remote command and control servers directly embedded in the malware's binary. We can simply modify these bytes, for example, in a hex editor, to change that address to point to our own command and control server. This means now when we take this malware and redeploy it, the malware will beacon, connect back to our infrastructure, and be ready for tasking. Now, as I mentioned, if the malware is a backdoor or an implant and expects to talk to a command and control server, well, if we're repurposing it, we're going to have to write our own custom command and control server as well. This will obviously ensure that when the malware checks in and connects back to us, we can give it tasking and fully exploit its remote capabilities. Now, such a custom command and control server really doesn't have to be anything incredibly fancy. Usually whip up a simple Python script. But if you're planning on deploying these repurposed malware samples to many targets, you might want something more comprehensively. At a previous demo, we talked about creating one such custom command and control server with the goal of analyzing a sample. Now obviously each specimen you repurpose is going to be different in the sense that it likely has a different protocol and thus will need a custom command and control server for that specimen, but that paper is kind of a good place to start. All right, so now let's walk through some actual examples repurposing some Mac malware. And we're going to start with a sample called fruit fly. Fruit fly is a rather unique piece of Mac malware. It was originally developed over 15 years ago, remaining in the wild and only very recently became detected. It's a fully featured backdoor which supports a myriad of remotely taskable capabilities, which really makes it the perfect candidate for us to repurpose. As we'll see, we can very trivially repurpose this malware, and then that gives us access to a proven, fully featured backdoor that we can utilize for our own subversive purposes. Fruitfly is actually written as a Perl script, though it's highly obfuscated. If we take a peek at the back door, we can see logic that processes command line arguments. That is to say, the script will check if it's been invoked with certain command line arguments, parameters, or flags. Turns out it's looking for a port or a port and IP combo of the command and control server to connect to. So this means if we specify our own via the command line, we don't actually have to modify the Perl script or the malware binary itself. So what we can do is we can persist this malware, Fruitfly, as a launch agent, and as we can see on the slide, we can pass in our address of our command and control server. So this means we can trivially repurpose this backdoor to connect to our custom command and control server, right? Because we can specify in the command line, we can now push that out, give the address of our own server, and the malware, when it runs, will connect directly back to us instead of the hacker's original servers. But to deploy this, we need an installer. Good news, previously I wrote one that's available on Pastebin. As we can see, it's just a few lines of code which persistently installs the malware in a manner that matches how it was uncovered in the wild. Finally, as I had previously written a custom command and control server to analyze the sample, we can just review this. So we're going to do a live demo now. Live demos are always risky. And actually we're going to run this on my laptop. This is my own personal developer laptop. I'm not going to run this in a VM. Because again, I want to show you the power of this repurposed malware, and once we've repurposed it, it's essentially trustworthy. So let's see this in action. So the first thing we're going to do is we're going to run the command and control server. This is listening for connections. And then we're going to execute the malware, specifically via the installer, passing in the address of our command and control server. When we run this, we can see that the malware now has connected to our command and control server on the right. And we see there's a myriad of capabilities that we can now task this malware. Again, this is running on my own personal box. So for example, if we execute command number 13, this will tell us where the malware is installed. We can see it's running out of users Patrick FPS odd. We can also do things like take a screenshot. That is command number 2. Execute that. We give it a parameter of 0, saying we want a full screen capture. And this will tell the malware, which has been deployed to my personal system now, to please take a screenshot and send it back to the command and control server. So we can kill the server, and we can open the screenshot, and we can see, yeah, it took an entire screenshot of the desktop. Okay, so that's Fruitfly. Now let's talk about repurposing a cryptocurrency miner, because maybe you want to make a lot of money mining cryptocurrency on other people's computers, but you don't have the skills, time, or resources to write your own. So our target is called Creative Update. This cryptocurrency miner was spread via Trojanized applications and then spread via the popular third-party application website macupdate.com. If we mount the malicious disk image that contains one of these Trojanized applications and reverse engineer the application's main binary, we can see it invoking a method called execute script with privs. And if we look at what this method does in a decompiler or disassembler, we can see it simply executes a file named script out of the application's resource directory. So if we take a peek at this script, we can see it first launches the real pristine copy of the application that it had Trojanized, for example, Firefox. And this is so the user who has downloaded this infected Trojanized application doesn't think anything is amiss. We can then see in the script it beacons out or connects out to a download server to download a zip archive named mdworker.zip. It then extracts this archive and persistently installs something named mdworker. If we look at the launch agent plist that persists the malware, we can see the path to the persistent binary, which is that mdworker binary we just discussed. Also, we can see some command line arguments that are passed into this binary. If we execute this mdworker binary, it turns out it's a legitimate cryptocurrency miner belonging to a company named MinerGate. The command line arguments therefore specify the miner account, that is where to send the mining results, and the type of cryptocurrency to mine. So similar to Fruitfly, since the relevant parameters are passed via the command line, as say opposed to directly embedded in the malware's binary, it's trivial to repurpose this sample. So first we simply modify the property list, the plist, to specify our own miner account, and then zip up the malware's components. Now instead of having the malware download that zip from a download server, we just add the archive to the applications bundle. This is far more simpler and self-contained. It means we don't actually need to set up a remote download server to host this second piece. Next, we tweak the script, so instead it utilizes the zip archive we just added. Finally, we repackage everything up and we're ready to go. So we're going to do live demo number 2. Bring up Finder window. First I want to show you the repurposed malware. It's kind of application bundle. We can see this is an app, and within the app there is this script file. There's the original Firefox. This is the one that's signed by Mozilla. If we pop over here though, we'll see that this is what the user downloads and expects to run. So what we're going to do is we're going to run this. This has been reconfigured. Again, I'm running this on my own personal system. I figured while I'm up on stage I might as well be mining some cryptocurrency. So we're going to run this. Firefox pops up. Everything looks great. The user is stoked. They've got this great browser. But now if we pop back to a terminal window, behind the screens, and make this a little bigger, we can see that the malware has persistently installed itself. And again, if we look at the program arguments, we can see that it's going to execute the miner named mdworker, but we have repurposed it so it's instead is going to send all the results of the cryptocurrency mining operations to me. Sweet. Awesome. All right. Well, since we're talking about making money, right? We all love to do that. Perhaps you want to deploy some ransomware without spending time writing your own. So now we'll walk through exactly how to repurpose KeyRanger. KeyRanger was the first fully functional in the wild ransomware targeting macOS. Hackers infected the popular BitTorrent client transmission on the legitimate application's website. This means that if users went to the transmission website to download the BitTorrent client, inadvertently they would get the malicious infected Trojanized version and become infected. Looking at the malware's binary code, we can see it executing something named general.rtf out of the application bundle. Though it appears to be a document, if we examine that file a little closer, it turns out it's not a document, it's really a mock-O binary. So what this mock-O binary does is first sleeps for a few days, and then it connects out to the attacker's command and control server, expecting a response consisting of an public RSA encryption key and then decryption instructions. It then uses that encryption key to encrypt the user's files and then displays the decryption instructions that demand a ransom. Pretty standard ransomware functionality. So let's talk about repurposing this ransomware. First, we're going to wait for 3 days. We're kind of in a rush to start encrypting people's files. So what we can do is we can just patch out, nop out the call to the sleep function. Pretty easy to do. and modify the addresses of the servers that the ransomware contacts for the public RSA encryption key and the decryption instructions. As we can see on the slide, these addresses are directly embedded in the malware's binary, so it's pretty easy for us to hop into a hex editor and change them to the address of our server. Pretty easy, right? And here for testing purposes, we just set them to localhost 127.0.0.1. Now, we also need a server because the ransomware is going to connect out when it's run, expecting that encryption key and decryption instructions. Turns out this is really easy to do. We can just take our own public RSA key and decryption instructions and package that up in a text file and then serve that up via netcat. So here's a demo of KeyRanger that's now been repurposed. We'll see in the terminal window, this is our server. Again, it's just netcat serving up the encryption key and the decryption instructions. The malware has been repurposed, though, to talk to this command and control server, not the attacker's original one. And then we'll start seeing the ransomware immediately start encrypting all the files on the desktop. Once the malware has done this, again, it's launched when the user launched the transmission application. They're not going to be privy to anything going on. You know, the encryption happens in the background, although they might see all their files being encrypted. So now when the files are encrypted, the user is going to be like, crap, this sucks. How do I get my files decrypted? They're going to open the readme.decrypt file, and you can now see we provided our own decryption instructions. So here I've said, hey, you know, sorry about losing all your files. Send me buckets of money and I will decrypt them for you. It's actually kind of mean. You know, maybe don't do that. The last sample I want to talk about repurposing is called Windtail. Now, Windtail is a lovely backdoor written by a rather sophisticated APT group. Here we'll repurpose both their exploit and their own backdoor to use for our own missions, our offensive cyber surreptitious processes. Now, one of the most interesting pieces of this attack was the malware's infection vector. And the way it was able to infect fully patched Mac systems was by leveraging a legitimate functionality of macOS by abusing something called custom URL schemes. Now, I've written a long, detailed blog that really dives into the technical underpinnings of this, but in a nutshell, on macOS, as soon as an application is saved to the file system, even before the user has run it, macOS parses that application, and if that application supports custom URL handlers, macOS will automatically register it. Once these custom URL handlers, or the app, has been registered, you can, for example, from a web page, make a request to that custom URL, which macOS will be happy to now launch. The exploit is realized in JavaScript. Basically, they have some code to first download a malicious application that contains a custom URL scheme. macOS registers that, and then they have some second piece of JavaScript which makes a request to that now registered custom URL scheme to launch the malicious application. In terms of the backdoor, so again, this is the payload of the exploit, they persist a login item that supports capabilities such as file collection and exfiltration. So if we fire up a process monitor, as we can see on the slide, we can observe what the malware does once it successfully infects the system. For example, we can see it invoking the built-in zip utility to compress the files that it has collected for exfiltration. And then via the built-in curl command, it sends them to the attacker's remote command and control server. The backdoor also supports a file download capability. So if we look at the SDF method, a disassembler or decompiler, we can see it decrypts the addresses of some embedded command and control servers. Then it makes an initial request to get a name for a downloaded file, and then makes a second request to get the actual file contents from the attacker's command and control server. If we use a network monitor, we can see this happening live. And as we note on the slide, the address of the command and control server is flux2key.com. And just remember this because we'll get back to this in a second. Now, once the malware has downloaded the file from the attacker's remote command and control server, if we look at more disassembly, we can see that it then executes this. So this is done within the same SDF method. We can see that it unzips the file it gets from the attacker's remote server via the built-in ditto command, and then it executes it via the NSTask API. So pretty standard built-in download and execute capabilities. Finally, the backdoor can be remotely uninstalled via self-delete logic. So every time the malware starts up, it connects to the attacker's command and control infrastructure and basically says, should I delete myself? If the command and control server responds back with a 1, the malware will first delete, uninstall itself, and then terminate. It's kind of a neat capability that allows an attacker to remotely disinfect targets. All right, so now it's time to coerce this lovely backdoor to do our own bidding. So first let's talk about repurposing the exploit. It's pretty simple to create a malicious web page that auto downloads a zip file containing a malicious application. As we mentioned, Safari by default will auto expand zip archives. So if we place a malicious application in that archive that implements some custom URL handlers, macOS will automatically register that even before the user has run the application. The malicious web page can then make a request to that now registered custom URL, which will cause the application to be launched. Now, there will be a pop-up or two, but the average user probably is going to click through these. So here's a demo of the repurpose exploit that will drop and persist Windtail. We can see the page has downloaded the application, and then we made that second request. There was a pop-up. Again, if the user clicks through, which some percentage of users will fall for, we can see that now the malware has been automatically and persistently installed. Again, since this is a logic flaw, there's nothing really for Apple to patch. So this still works on the latest version of macOS. So now we've repurposed the exploit, let's talk about repurposing the malware, because it doesn't really help us if we are spreading their original malware. That still beacons back to the attacker's command and control servers. So step 1, we need to modify the embedded command and control server addresses so that when the malware is deployed via our repurposed exploit, it connects to our servers so that we can task it. Unfortunately, the embedded addresses of the malware's command and control servers are encrypted. Not to worry, what we can do is we can coerce the malware to always load a dynamic library, and then once our library is running in the process address space of the malware, we can basically modify the malware at runtime to intercept the decrypted addresses of the command and control server before the malware uses them to connect out. So let's look a little closer about how we accomplish this. Again, the goal is for us to specify our own command and control servers so that the malware connects back to our infrastructure. So our dynamic library has now been loaded into the address space of the malware. What we can do is we can swizzle or swap out the malware's decryption routine. It's a method named yoop. This is accomplished via the rather powerful method exchange implementations API. As we see on the slide, once the decryption function has been swizzled or swapped out, whenever the malware invokes the decryption function, transparently the Objective-C runtime will actually now call our method in our library. What our method now does is calls into the original decryption routine, and I have no idea what the decryption algorithm is or how it works, and frankly I don't care. But what I can do is, since it's swizzled and passing through us, I can see the results of that encryption. So if the original decryption method returns the decrypted addresses of the command and control servers, I can just return my own command and control server back into the malware's logic. So this dynamically gives us the ability to transparently swap out the decrypted command and control servers with our own. And the malware is none the wiser. Now I added some debug messages to the library, so if we execute this now repurposed malware, we can see and watch this at runtime and view the addresses of the command and control servers being swapped out. So at the bottom of the screen, in the terminal output, you can see that our library, which is called through to the original decryption method, has detected that that response is the command and control server that's now decrypted. We don't want to return that to the logic in the malware that's trying to connect out, so we basically just drop that and return our own. Again, this ensures now that the backdoor will always communicate with our servers instead of the original APT groups. Now, we still have to write a command and control server because the malware will now be connecting back to us, but we have to be able to talk the protocol so that we can correctly task it. Now, the main feature of the Windtail backdoor is to collect and exfiltrate files. So let's add this first to our custom command and control server. Files are exfiltrated via post requests. So we simply write a few lines of code in Python to handle this, saving off each file the malware sends to us from the infected host. So here's a demo now of our custom command and control server receiving exfiltrated files from the attacker. On the left, you can see the network requests coming in, and on the right, all our command and control server does is write these out to the file system. This means we now support the ability to respond to the malware as it exfiltrates all sorts of files off infected hosts. Let's also extend our custom command and control server for this Windtail implant to support the download and execute capability. So we noted the malware makes two requests for this. The first is a request where the expected response is for the name of the downloaded file. And then the second request, we need to respond with the actual bytes of the file we want to download. The malware will then save that to the file we specify and then unzip that and execute that. Now again, we only need a few lines of code in Python. You can leverage a lot of built-in Python libraries to do this. And once we do that, we then have the ability to task the implant. So let's watch this in action. We're going to see the malware connecting out to our command and control servers because we've swapped out those addresses. And what we'll do is we'll have it download and execute the ubiquitous calculator.app. So here comes the connections. We're giving it calculator.app. This could be any binary, and then the malware will unzip that and execute that. Now, armed with this remote download and execute capability, this means we can install other tools or even second pieces of malware. So it really makes this repurposed implant kind of infinitely extensible. Finally, let's add the ability to our custom command and control server so we can support the self-delete command. Because at some point, if the FBI comes knocking on your door, it might be really nice to just press a button and have all these infected systems uninstall themselves. It's trivial to support this functionality. Basically, when the malware connects out, checks in with our server and asks, should I self-delete? We just respond with 1. This will tell the malware to delete and fully uninstall itself. This is another demo showing this in action. We can see the persistently installed implant. It's that orange logo. The application originally tries to mimic a PowerPoint documentation. Kind of sticks out, but this is in kind of a hidden system directory. What's going to happen is the malware is going to connect out to us, make the should I self-delete command a request. We're going to respond with 1, which will cause the implant to uninstall itself and then terminate. So we can see it disappear and then it stops beaconing because obviously it's just self-deleted. All right, so we've showed exactly how to repurpose a myriad of Mac malware. We talked about backdoors, ransomware, cryptocurrency miners. Although we still need to talk about how to remain undetected. As generally speaking, we're repurposing known malware, which means both macOS and third-party AV products likely will block or detect these unless we do something about it. So first up, let's talk about macOS's built-in malware mitigations such as Xprotect, the malware removal tool, and code signing certificate checks. Now, at first glance, these might seem somewhat problematic as they may generically block our repurposed malware on any, or rather on all Macs. Again, we really need to talk about bypassing these because if we went to deploy a nicely repurposed piece of malware and Apple blocked it, that would kind of suck. So let's start with Xprotect. Xprotect is a simple signature-based AV scanner that's built into all recent versions of macOS. Somewhat limited, it only scans files downloaded by the user the first time they're executed. If we look at their signatures, they're in a file named xprotect.yara. We can see various Yara signatures to detect common pieces of Mac malware. For example, KeyRanger, the malware we just talked about repurposing. Now at Digito, we wrote a simple utility called UXProtect that allows you to explore these signatures via the UI, as well as at any time basically scan arbitrary files against these built-in signatures. Now, since XProtect is purely a signature-based detection mechanism, it is incredibly trivial to bypass. So let's take a closer look at the signature for KeyRanger. We can see it maps to a group of instructions in the malware. Knowing this, to bypass the signature, we can simply reorder or modify any of these instructions. This will change various bytes, which will of course cause the signature to no longer match. So here, for example, we simply change the number of bytes that may be written to a buffer from OX400 to OX300. Now, this doesn't impact the malware's functionality at all, but as we've changed the bytes that the signature is looking to match on, we've completely thwarted the XProtect signature. Demo time. Here we have two instances of KeyRanger. Again, it was distributed in this infected transmission BitTorrent client. On the left, we have the original sample. This is the hacker's sample. And on the right, we have the repurposed sample that's going to talk to our own command and control servers to get the encryption key. And then also, it has that 1 byte modification to bypass XProtect. So we're going to launch both of them. We're going to see the original one is detected by XProtect and blocked. There's no option to run it. The user has to click cancel. If we execute the second one, it's going to say, hey, this is downloaded from the internet. Are you sure you want to run that? User clicks yes. The ransomware is now able to persistently install on the user's system and immediately starts encrypting all their files. Whew. But wait, there's more. Next up, we have code signing checks. So most binaries on macOS are code signed. Signed binaries are not blocked by Gatekeeper, thus a lot of Mac malware is now code signed. The downside from the malware's point of view is once this malware is detected, Apple can simply revoke the code signing certificate, and this means the malware will not be able to execute on any other Mac. So here, for example, we can see we have the Windtail binary, and the original code signing certificate has been revoked by Apple proper. This means even if we repurpose this and attempt to redeploy this to new systems, it won't be allowed to run. Well, the problem is really the revoked certificate. It's not the malware per se, so we can simply remove the code signing certificate. And then either distribute the repurposed malware unsigned or re-sign it with another legit developer code signing certificate, which is pretty easy to get. So to unsign it, Apple actually provides a utility called CodeSign. There's an undocumented flag -remove signature. So if you execute this and point it at the malware, Apple's utility will nicely strip off the revoked code signing certificate. And then, as I mentioned, we can just deploy it as is, unsigned, or if we want to get a little more fancy, we can re-sign it, again using the CodeSign utility, passing in the -s flag. This means the re-signed Windtail will now no longer be blocked by macOS. Finally, we have MRT. This is Apple's malware removal tool. It's another built-in AV-like tool that ships with all versions of macOS. It's similar to XProtect, but scans malware that may be already on the system, and if it detects it, it'll automatically remove it. Now, unlike XProtect, its signatures are directly embedded in its binary. Kind of interesting. And as an interesting aside, Apple also uses MRT to remove legitimate software it deems unsafe, such as the recent Zoom application that had some vulnerable components. So giving a lot of power to Apple here for them to arbitrarily remove files from your system. Now, since MRT, like XProtect, uses signatures, it's equally trivial to bypass. If we dump the MRT binary, because again the signatures are embedded directly in that binary, we can see all the signatures, including one for fruit fly, which makes us wonder, is this going to detect our repurposed fruit fly malware? Well, if we examine the embedded MRT fruit fly signature, we can see it's detecting fruit fly based on both the path of the malware and its launch agent plist. This means as long as we change either the path or the name of the malware, it's not going to detect it. Like I said, trivial. Now, I also want to briefly mention bypassing third-party antivirus products, because you might run into a system where the user you're targeting has an antivirus product installed. Now, there's been a lot of talk about this, so I'm not going to dive into it a ton, but suffice to say, traditional AV products that largely rely on signatures, which is pretty much the norm, especially on Mac OS, are equally trivial to bypass. For example, I took Fruitfly. Recall it's a Perl script. I ran it through a free online Perl obfuscator, which caused detections on virus total to drop all the way to 0. Now, that works, but you might want to use more sophisticated capabilities, especially for the binary-based malware. So you can do things like pack them, use a custom encryptor, or even in-memory execution. Now, I gave a talk at Black Hat a few years ago about these techniques. Recommend checking that out, because that can ensure that even if the user has a third-party AV product installed on their system, it will be unlikely to detect your repurposed malware creation. Now, for Mac users, this kind of sucks, right? We showed that advanced adversaries are already using repurposed malware samples. And then it's actually not that difficult to do. Oftentimes, we just have to switch a few bytes or change the command line arguments, and now, power to the people, we have the ability to take these very sophisticated threats and redeploy them for our own surreptitious processes. Also, the majority of detections, those built into Mac OS or those provided by third-party AV products, fail to detect these repurposed threats. This, in my opinion, is rather lame, because if you think about it, this repurposed malware is basically an exact copy of the original known malware. We've really just slightly reconfigured it. So I want to end this talk, kind of switch gears. We'll put on our white hats now and talk about how to generically detect such threats. So first, and this is a well-known fact that I hopefully just illustrated, detecting malware based on signatures, bound to fail. So instead, what we need to do is look for unusual or malicious behaviors. By definition, malware does unusual or abnormal things. So let's leverage this fact to discuss generically detecting even repurposed threats. Because again, as we just stated, if we or an attacker repurpose a known piece of malware, the underlying functionalities, its behaviors and capabilities aren't going to change. That is to say, even a repurposed piece of ransomware is still going to encrypt all your files. A repurposed backdoor is going to persist and then start exfiltrating your files to a remote server. So here on the slide, I've kind of listed some capabilities or some actions or events that are good to look for and monitor, because they may provide insight into generically detecting even repurposed malware. So let's start by talking about persistence. What I mean by persistence is the way that malware installs itself so that it's automatically restarted every time the system is rebooted. This is something the majority of malware, both on Windows and Mac, strives to achieve. So what we can do is we can simply monitor the file system, specifically observing persistence locations, and then if anything modifies those, we can alert the user or a sysadmin and say, hey, look, something just persisted. Maybe you want to take a closer look at it. So here, for example, we can now alert and generically detect when WinTail, either the original or the repurposed item, persists. Next up is mic and webcam access. A lot of Mac malware accesses the webcam or the mic to spy on the users of an infected system. So to detect this subversive activity, we can register with Mac OS. It turns out there is a callback you can register that anytime anybody accesses either the mic or the webcam, you will programmatically get notification of that fact. So this will allow us to detect malware, even something like Fruitfly, which we've repurposed, or an exploit like Zoom, anytime it accesses the mic or the camera. Next up, we have keylogger detection. Malware oftentimes tries to capture your keystrokes to steal things like passwords and credit card information. On Mac OS, the easiest way to capture keystrokes is by registering something called an event tap. What we can do is we can generically detect these taps by, again, registering for a dispatch notification that will be kindly invoked by the operating system anytime a new event tap is installed. This allows us to very trivially detect keyloggers even if they have been repurposed. We talked a lot about Fruitfly. This is one of the more sophisticated feature-complete malware. One of the neat features that it has is the ability to remotely interact with the UI via synthetic or programmatic mouse and keyboard events. So the attacker can move the mouse, click on buttons, or even send programmatic keyboard events to an infected system. So this is something we want to detect because this isn't something that should normally be happening on a Mac system. Luckily, it's pretty easy to detect. We can install our own event tap and monitor for mouse activity. When a mouse click is generated, we can then examine a variable, a state variable, which macOS sets to 1 if the mouse event, the click or the move, has been programmatically generated. So this allows us to now generically detect synthetic clicks even in repurposed malware. Now, at the start of the talk, I mentioned I was the creator of Objective-C. This is my kind of personal Mac security webpage. But the main goal of Objective-C is to provide free and largely open source security tools for end users who are using Macs. Many of the detections we talked about are realized in tools on this site. So if you're interested in that, hop over to objectivec.com. Now, a downside of these tools is they're all separate, right? There's an individual keylogger detector, there's an individual firewall, there's not like an all-in-one solution. So when I started working at Digita, we decided to combine these into a single all-in-one tool. And the idea was to monitor the system and then create rules to detect unusual behavior. We then took both those pieces and fed them into Apple's built-in game logic engine, which would do all the hard work for us and would evaluate our rules on top of our data and spit out a result for us. So now let's talk about some of these behavior-based detection rules. And it's important to note you can use these in other security tools as well. So this is not specific to our product per se. So using this system, we can generically and rather trivially detect all the repurposed malware we talked about today. So for example, Wintail, we can detect its exploitation vector by observing the fact that Safari downloads and then auto-extracts an application. That same application then triggers the registration of a custom URL handler. And finally, then that same application is started automatically via custom URL request from a website. So detecting the combination of those events gives us a generic capability, both against Wintail or any other malware that utilizes this same infection vector. Similarly, we can detect Fruitfly at install time by observing various events that cumulatively indicate something is suspicious or at least amiss. So here, for example, we observe the fact that a hidden non-Apple binary has persisted as a launch item. There's no legitimate reason that this should ever happen. So that's really shady. Now imagine that Fruitfly is already running on the system. We can also detect this by observing runtime behaviors. For example, Fruitfly does things that are really shady and suspicious. For example, as we mentioned, persisting and running a hidden process. This hidden process in some scenarios will drop an embedded unsigned binary to the temp directory, execute that, and then start capturing or generating synthetic events. Clearly, this is incredibly shady. Now, of course, we don't have to trigger when all these events occur. We can look at them either cumulatively. We see one or two, we might want to take a closer look at the system because something might be amiss. So hopefully I've illustrated that by using these behavioral heuristics, we can generically detect even sophisticated Mac threats, even those that have been repurposed by advanced adversaries or by Patrick. Now, before I end this talk, I'm really excited to announce Objective by the Sea version 3.0. As some of you are aware, Objective by the Sea is a Mac security conference that I organize each year. This year it'll be back in Hawaii. So if you want an excuse for your company to send you to Hawaii in February, go to objectivec.com. Well, that is a wrap. I want to thank you all so much for attending my talk. We have about 2 minutes for questions, and then I will also be off to the side of the stage if you want to come up and chat, talk nerdy about Mac stuff. So again, thank you though for attending. I really appreciate it.